Hello, students. We are here to discuss uniform circular motion. Uniform circular motion. We are going to start by looking at examples of circular motion. So the first example we have is a ball that is moving in a circle after being whirled. So it's a whirling ball. So a whirling ball will be example number one. Example number two will be the car that is moving around a curve. So that demonstrates circular motion. And we have example number three that shows a spaceship that is orbiting the Earth. So that's the third example. We have a lot of examples in everyday life that demonstrates circular motion. So I would like you to think about those examples and list any other examples. So any other examples. So think about it, any other examples, and you can list those examples somewhere in your notebook. All right, so let's move on. We have a teaching problem here. We would like to understand better circular motion. We are going to understand this circular motion by looking at a cube that is sitting, that is on the flat table surface, and it's actually frictionless. We connect it to, this is what is a string, and this string goes through a hole, and then we can actually spin the cube on top of the table. And we can try our best to make sure that the cube moves at a constant speed. Now we have some few questions to answer here. The first question says, if the cube is moving at a constant speed, does it mean it's moving at a constant velocity? Well, the answer is that, well, you might want to pause the video and think about what will be the answer for that. But as you remember, velocity is defined as speed in a given direction or speed in a specified direction. In order for us to define velocity, we have to talk about the speed of an object as well as the direction. So in this case, we know that although the speed is constant, the direction is not. For example, right now here, I may have my velocity as this. This is a linear velocity or tangential velocity, like that, the radius of curvature there. And when the cube is somewhere here, the velocity will be this direction, straight line. Okay, and this is my radius of curvature. When the cube is right here, as you can tell here, the direction, the velocity, sorry, this is V, this is V, and right here, the direction is this way. Okay. I'm trying to make the magnitudes the same to make sure that it's constant speed. All right. So as you can see, I mean, roughly you can see that the direction is changing. So therefore, we can say that, does it mean it's moving at a constant velocity? The answer is no. Direction is changing. So direction is changing. So the answer is no. All right. Is the cube accelerating? Is the cube accelerating? Well, you might think about it like, oh, okay, maybe because the speed is constant, then it's not accelerating. But wait a minute, we need to remember the definition of acceleration. Acceleration is the change in velocity over time, or the change in velocity with the rate of change of velocity with respect to time. So here is the velocity that matters. If the velocity is changing, then therefore the cube is accelerating. So yes, because velocity is changing. So we see that because velocity is changing. And now this kind of acceleration is called centripetal acceleration. So we call this one centripetal acceleration. or center seeking acceleration. Centripetal acceleration. And in terms of formula, we can find the centripetal acceleration A sub C as V squared divided by the radius of curvature. So that is the formula for centripetal acceleration. We are not going to verify it here or to prove anything here, but we just give it as it is. So that is the formula for centripetal acceleration. By the way, the term centripetal, it means center seeking. You'll hear this definition, term a number of times. When we say centripetal, it means center seeking. Let me write it here. Okay. So can I write here? What's going on? Okay. So when we talk about centripetal, this refers to center seeking. So it is always directed towards the center. So as you can see, if I look at this situation here, the direction of acceleration right now here will be towards the center. If I am right here, the direction of acceleration will be towards the center. If I am on the third position here, direction of acceleration is always towards the center. That's why this kind of acceleration is called the centripetal acceleration. Okay. All right. So now the next question: draw a force diagram of the moving cube and demonstrate the application of Newton's second law of motion to uniform circular motion. I'm going to draw the side view of the situation. This is the table surface. And I have my cube here. We have gravitational force pointing downward always. And we have the normal force, support force acting on the cube. And we have also this force pointing to the left. This force is actually the force of tension. That's tensional force acting on the cube. Now, if we want to apply Newton's second law to this problem, we are going to write the net force must be equal to mass times acceleration. I'm going to focus on the x direction because the net force in the y direction, this direction, is 0 because the object is not moving up and down. It's not accelerating up or down, I should say. So the net force in the y direction is 0. So my focus is on the net force in the x direction. Now the net force in the x direction is actually t, but it's pointing to the left. I'm going to put minus t equal to mass. And now the acceleration in the x direction at that point, acceleration is towards the center. If you remember, we are drawing the situation from here, like from here or here. If you see that the direction of acceleration is towards the left at that point, then we can put a negative sign right here. So we're going to say minus. Now remember, we just said that acceleration is given by v squared over r. So that will be v squared over r. The minus sign means pointing to the left. The negative sign is available on both sides of the equation. So we can drop it, or we can divide both sides by -1. The negative sign will drop. So you end up with, may use a different marker. We'll end up with the tension is equal to mv squared over r. So this is the tension. And in general, this tension is the one that is providing the centripetal. It's actually representing the centripetal force. So we can also write that the centripetal force is mass times velocity squared divided by the radius of curvature. Remember, This mass is the mass of the cube. Velocity is the linear velocity or tangential velocity. And R is the radius of the circle or radius of curvature. And this defines the centripetal force. Okay. We are moving on to the next example. So this example, they are telling us that let's find how tension will change if we try to reduce the radius to 1/4 of it. So we are trying to reduce the, oh, sorry, take it back a little bit. Okay, we are trying to reduce the circular path a little bit, make it smaller. Okay, trying. So what will happen to the tension force? Imagine we just reduce the radius curvature to 1/4 and try to find out how the tension will change. So remember, we can go ahead and say tension. Tension, original tension will be mass times v squared, which is constant, divided by original radius of curvature. That will be original radius of curvature. Okay. And then what we are thinking about, we are saying, okay, let's take the original radius. It should be now 1/4. Or I mean, let's take the radius to the new radius to be 1/4 of the original radius. Let me do this. So we are going to write here the new tension will be mass will be the same, velocity will be the same. Now divide by the new radius. So the new radius, Rn, represents the new radius. Now we know the connection between R0 and Rn. In other words, original radius and the new radius. What's the relationship? Think about what's the relationship between the new radius and the original radius. The relationship from the problem, it says that the new radius is now equal to the original radius divided by 4. This is what it means from the problem here. So let's go back and see what they're saying. They're saying that what happens to the tension force if the radius of the circular path is now what? 1/4 of the original. So we are taking the new radius to be 1/4 of the original. So that's why I'm saying Rn, the new radius, must be equal to R0 over 4, right? So for that reason, we are going to rewrite this equation, this one. It will be the new radius will be mv squared over what I was saying, the original radius divided by 4. So like that. All right, so that means what? It means we can go ahead and say, okay, it means the new tension will be mv squared. Some people write this one, divide by original over 4. And we can rewrite this as mv squared. We can change the division into multiplication and reverse these numbers like this. Remember what we do? So we multiply here 4 over R0. So that gives you 4 times and then mv squared divided by R0 right there. All right, and notice that this quantity here represents the original tension. If you remember, the original tension was written like here, So that's original tension. So what I'm saying here is that we can rewrite this as 4 times original tension. So in short, the new tension is 4 times the original tension. So the new tension is 4 times the original one. In other ways, what we are saying here is that the tension will be quadrupled if you reduce the radius of curvature to 1/4. So the new tension is 4 times. In order to maintain the speed, you need actually to make sure that the tension in the rope has to be 4 times more. All right, so let's look at the other question. I don't have space here, so I might have to erase all this stuff. All this stuff has to go. Okay. All right, so what's the other question? The other question is, what happens to the tensional force if the radius of the circular path is kept constant, but the speed is doubled? What happens to the tension force if the radius of the circular path is kept constant, but the speed is doubled? So we're going to do the same approach. We'll start with the T original is M. Now this time around, we see that it's the velocity that is changing. So we're going to put original velocity squared. The radius is constant, so just put it R. M and R, no subscripts because they are not changing at all. What is changing is the original speed, and therefore it changes the tension force. And we write the formula for the new tension. The new tension will be M. Now, what will happen to V? The problem tells us that we're changing the speed to be now double. So double 2V naught. Now let's look at the problem again. They said, what happens to the tension force if the radius of the circular path is kept constant? So we keep constant, but the speed is doubled. So that's why here I'm saying that V naught goes to twice V naught. So we are doubling the speed. So I'll put twice V naught here, close bracket, then that will be squared, divided by radius is not changing here. So now it's a matter of rewriting this so that we can see the effect of changing the velocity. Now, rewriting that, I'll put it here. The new tension will be M. Now, the squared part gives us 4 because 2 squared is 4, and then V naught squared will be here and divide by radius R. I can take the 4 somewhere here. I'm just multiplying parameters here, so I can shift the 4 there. That will be 4. The rest will be, I'm remaining with the mass. There is V naught squared divided by R. So this looks like the original tension. So I can say now that the new tension will be 4 times the original tension. So what we see here, again, we see that tension will be quadrupled. So if we do that, tension will be quadrupled, or multiplied by 4 times will be quadrupled. Yeah, or it is 4 times more. Okay. All right, so that's the discussion regarding these questions. We're just trying to understand how tension or how the centripetal force behaves if we change the radius or if we change the velocity. We can also have other questions. What about if the mass is changing? We just have to use some algebraic reasoning to understand how tension behaves. All right, now let's look at this problem here. A car is moving on a frictionless banked curved road. Show that the horizontal component of normal force on car provides the centripetal force. Show that the horizontal component of normal force on the car provides the centripetal force. It's a teaching problem. Now, remember the normal force has to be perpendicular to the surface. So if I draw it like that, that's the normal force. It has to be perpendicular. So I'll try to put it to make it perpendicular. Okay, so that's the normal force. That's the normal force. Now, the horizontal component of this will be as follows. So I'm going to use a red marker. So this will be a horizontal component. It has to be horizontal to the surface here. So that's horizontal. I'm going to put N sub H. That's the horizontal component of the normal force. And the vertical component, I follow it here. The vertical component of the normal force will be here. So this will be NV. I don't know if that V is clear, but it's NV. That's the vertical component of the normal force. And as you can see, if you remember the rules we established, that's like a parallelogram. Okay. All right, so I have broken down the force into different components. Now I have to remember that the normal force is not the only force acting on the car. There is also gravity, but gravitational force must be actually equal to the normal force in the vertical direction. All right. Let me try to draw the forces. It would be nice to show them. The normal force has to be somewhere. Okay. All right. So using a red color. So we have okay, so I'll draw it again quickly. So that's the normal force here. And I'm trying to draw from the center of the car to make sure that gravity is somewhere there. And the components, draw the component in the vertical direction. And then another component has to be horizontal. So this is the horizontal component. Horizontal component. Okay. So I have broken down the normal force into the vertical and horizontal component. That means I don't need this one. I can now tell that the normal force in the vertical direction balances the gravitational force here, mg. So it balances gravitational force mg. There's no motion up and down there. And we have the normal force in the horizontal direction. That is the one that is providing the centripetal force. It is actually providing the centripetal force, and that is actually the mass of the car. Its velocity squared divided by the radius of curvature of the banked rod. Okay. All right, so we just understand that in this case, the normal force is provided by the horizontal component of the normal force. I mean, in this case, the centripetal force is provided by the horizontal component of the normal force. Okay, let's look at one more example. Here is an example. A ball revolves in a horizontal plane as shown at a constant speed. That's a conical pendulum. what is the direction of acceleration and what force causes the acceleration? It's a teaching problem. Well, first of all, we need to understand that tensional force has to be drawn like this. So there's tensional force here, T. And then we can break down tensional force into a component that is along the plane of the circular path. That will be tension in the horizontal direction. And then there is also a component upward, this one, that will be tension in the vertical direction. You might want to use different colors to show that these components of the tensional force. So we have tensional force, but also we have the force of gravity pointing downward. So there's gravity, but this has to balance the tension in the vertical direction. So this is G, right? So in this case, we see that since the ball is not moving or accelerating up and down, we can say T, tension in the vertical direction, balances the weight, or mg. And then in the horizontal direction, we have tension. The component of tension in the horizontal direction must be equal to the centripetal force. And this is actually providing the centripetal acceleration, v squared over r. So to answer the question, what is the direction of acceleration? The direction of acceleration will be towards the center. As you can see here, it's towards the center of the circular path. And what force causes the acceleration? The force that is causing acceleration is the component of the tensional force in the horizontal direction. So this is what is causing the acceleration, the tension force, a component of the tensional force in the horizontal direction. Okay, let me see if I can, if I have space to write this one. Maybe I should write the answers here. So if this is part A, what is the direction of acceleration? So A will be towards the center, of the circular path. If the other part is B, if the other part is B, this is B here, then how do I answer that? Or what causes this acceleration? So this acceleration is caused by the component of the tensional force, the horizontal component of tension. Let's just say that. The horizontal component okay, and that is actually IE T sub H. Okay, so I have some problems for you to try. So try this one out. You might want to pause the video, take a picture of this, and try this problem. The problem says a ball revolves in a horizontal plane as shown at constant speed. It's a conical pendulum. The question is it possible for the string to lie in the horizontal plane? I'm talking about this string here. Is it possible to lie in the horizontal plane? In other words, if you are swinging or whirling, I find it difficult to pronounce this one, whirling, if you are whirling a ball on top of your head, is it possible for the string to be exactly horizontal? Is it possible? And what does that mean? Now, there's a hint here. They say, think about the following questions. What is the direction of acceleration? And what force causes the acceleration on the ball? And what force balances the weight of the ball? So is it possible Maybe if you swing very fast, is it possible? But most of the time when you try to whirl or swing something on top of your head, we see usually the string, it's usually at an angle with respect to the horizontal, or the angle with respect to the plane of a circular path. Now, my question is it possible? Can we swing it as fast as possible, and then we may, we make the string to be horizontal with the plane, with the surface? So think about it. Question number 2 is similar to what we discussed. You are whirling a cube on a frictionless stable surface. What happens to the tension force if the radius of the circular path is halved and the speed is kept constant? B, if the string breaks, what will be the immediate path of the cube? You can show that on the diagram here. What will be the immediate path of the cube? So assuming that is you're swinging, maybe initially the direction is this one, and then it breaks. What will be the direction? So think about, will the direction be this one, or will the cube go this way? Will the cube go downwards, or will the cube go this way? So you have so many options, or it will go this way, or it will go that way. Okay, so let's assume that this is option 1, option 2, option 3, option 4, option 5, option 6. Where will the ball go? What's the immediate path? Imagine that the string breaks whilst you are spinning the cube. Where will the ball or the cube go? So that is your exercise to think about. All right, so this marks the end of this discussion. If you have any question, please feel free to reach out to me. Thank you.